Howdy, this video on section 5.5 will include one-place predicates and two-place predicates. This is part of our introduction to predicate logic based on the textbook by Suppes and Hill. I'm the amateur logician. Here's an example of a simple atomic sentence in predicate logic, perhaps the most famous of them all. Socrates is a man. Where man, of course, is a predicate, and as such, it's describing our particular term, namely Socrates. In this case, Socrates, the term, also happens to be a subject, or the subject. But it's actually not necessary in predicate logic that a term is also a subject. And in fact, there can be more than one terms attaching themselves to a single predicate. Now, in this example, we have a so-called one-place predicate. And in the next slide, I believe, we'll look at an example with a two-place predicate. But in any case, we have the English sentence, Socrates is a man. The predicate is man, and to put it into predicate logic, we will symbolize man with a capital letter, such as M, and for the term, we always symbolize it with a lowercase letter, such as lowercase s. Moreover, we have variables, and variables can be used as terms, but they don't stand for particular names. So clearly with this lowercase s, we're talking about a particular person, namely Socrates. In general, X, Y, and Z are reserved letters for variables only. They don't stand for a particular name. But here's an example to make this more clear. From the textbook on page 191, X is an even number. So even number is our predicate. We can give that a capital E. And we have X as our variable. It's a reserved letter. So it doesn't stand for a particular number, such as 2 or 4 or 6. Just any number that happens to be an even number. Now I should note that strictly speaking, when you have these variables, they must be quantified. They need a quantifier to be appropriately written. So this statement here is really no good, strictly speaking. We would have to write something such as, there exists an X such that X is an even number. So here we have our quantifier. Any variable has to be quantified. And we'll talk about this in a future section. Now a term can be a variable or it can reference a particular thing. So clearly with X, Y, and Z, we're talking about variables. And when we're talking about particular things, we have something such as Socrates. Now as you know, if we have a capital letter, we are representing a predicate, whereas if we are using a lowercase letter, we are representing a term, or we might call it simply a noun phrase or noun phrases. In our last slide, we dealt with what we can call a one-placed predicate. For example, Socrates is a man. It's one-placed because you only have one term, namely Socrates, that is attaching itself to the predicate. But here's an example from the textbook where we have something that's two-placed. We have a two-placed predicate. We have Eisenhower appointed Chief Justice Warren. We have Eisenhower, who is the subject, but we also have Chief Justice Warren as a noun phrase or a term. So there's really two noun phrases where appointed is our predicate. In general, we might think of it this way. X appointed Y, where appointed is our predicate, and we have to have a capital letter for that. For example, A, where X and Y stand for particular people. We have E for Eisenhower, lowercase e, and lowercase w for Chief Justice Warren. And then we can construct our predicate logic, capital A, lowercase e, lowercase w. Eisenhower appointed Chief Justice Warren. You could have two-place predicates, one-place predicates, but you can also have n-place predicates. It's really unlimited. Here's another example, which is a little different. Bill helps Harry and is helped by Jack. Well, in this case, we have this and. So really, we have a molecular sentence composed of two atomic sentences. We have atomic sentence here, and we have an atomic sentence here. Our first atomic sentence, Bill helps Harry. Helps is the predicate. And we have two terms here. We have Bill, we have Harry. Moreover, for our second atomic sentence is helped by Jack. We have helped as our predicate, and Jack as our term. In general, we might think of it as this. At least on the left-hand side, we have X helps Y, where B is for Bill, H is for Harry, and J is for Jack. And we can then construct our predicate logic, capital H, lowercase b, lowercase h, and uppercase H, lowercase j. All right, let's jump right into exercise 8b from the Suppes and Hill textbook. These all happen to be molecular sentences, which means they are composed of individual atomic sentences, and our goal is just to translate these sentences into our mathematical predicate logic. The only way to get good at this stuff is to see many examples and to practice. Number one, if the natalist is in equilibrium, then either it is at rest or it is moving at a constant speed in a straight line. We'll notice overall we have a conditional, if then, and in our consequent we have a disjunction with the or sentential connective. Let's count the number of atomic sentences. We have the natalist is in equilibrium. That's one atomic sentence. It is at rest is another atomic sentence. It is moving at a constant speed in a straight line is another atomic sentence. In terms of the first atomic sentence, the natalist is in equilibrium. In equilibrium is the predicate, so we'll give this a capital E. The term, the subject, is the natalist, so lowercase n. We have our conditional, so we need our arrow. It is at rest. At rest is our predicate, so we'll give that a capital R. It refers to the natalist, so we'll give that a lowercase n. We have a disjunction, so we have the or sentential connective. It is moving at a constant speed in a straight line. We can say moving at a constant speed in a straight line is capital M, that's the predicate. The name is the natalist, so lowercase n, and we can put parentheses around our disjunction there. Number two, Martha loves Don, and Don loves Martha. We have a conjunction with two atomic sentences. This time we have two-place predicates. Martha loves Don. Loves is the predicate, but we have two names here. So we have Martha, lowercase m, and Don, lowercase d. I should say order counts in this case. So we have Martha loves Don, so MD. We can say DM. Order counts. We have our conjunction, so we have the and sentential connective. Don loves Martha. Loves is the predicate, so capital L. We have two names, so lowercase d for Don and lowercase m for Martha. Order counts. Number three, either Mrs. Clark gives Walter a ride or he is late to his appointment. We have the predicate, gives a ride. We'll give that capital R. We have two names, Mrs. Clark and Walter, so we'll give this lowercase c, lowercase w. We have our disjunction. He is late to his appointment. Late to his appointment is the predicate. We'll give that a capital L. He refers to Walter, so we'll give that a lowercase w. Number four. If the elastic limit of the spring is exceeded, then its molecular forces are overcome, and the spring does not return to its original form. With this example, I think it points out the fact, implicitly at least, that oftentimes translating is an art. It's not an exact science, so I can see different ways you can translate this, but here's one way, and then I'll talk about another way. Because here it's not clear what should be not treated as the predicate, that's the easy part, but what should we say is the individual term, or terms, or the names. So we have the elastic limit of the spring is exceeded, so that seems like a good predicate, so we'll give that a capital E. And then for the term, we could say the elastic limit of the spring, so lowercase e. On the other hand, I can understand why someone would say just the spring and give it a lowercase s. Next we have our conditional, so we have the arrow. Its molecular forces are overcome. It's the predicate, so capital O, molecular forces, we can give that the name, so lowercase m. But once again, I can understand how we might want to combine molecular forces are overcome as the predicate and its referring to the spring. Once again, you know, it's an art form translating sometimes. We have the conjunction and. The spring does not return to its original form, so we have the negation. Returning to its original form is the predicate. We'll give that a capital R. And we have the spring for the name, lowercase s. And then we can get some parentheses in there. Number 5, if either Joe is not the brother of Maria, or Maria is not the sibling of Joe, then Mr. Lopez is not the father of Joe, and Joe is the cousin of Maria. A lot going on there. There are 4 individual atomic sentences that compose this molecular sentence. We have a conditional overall, and if then. The antecedent, we have a disjunction. We also have 2 negation signs. And in the consequent, we have a conjunction with 1 negation sign. Joe is not the brother of Maria. We have a negation, so let's insert that in. Not. Joe is the brother of Maria. Brother of. We have the predicate. Capital B. We have 2 individuals referred to. Joe and Maria. So we need lowercase j, lowercase m. We have our disjunction, so or. Maria is not the sibling of Joe, so we have a negation. Maria is the sibling of Joe, sibling of is the predicate, capital S. Maria, lowercase m. Joe, lowercase j. So this is the antecedent to a conditional. Mr. Lopez is not the father of Joe, so the negation. Father of is the predicate. Mr. Lopez, we'll give that a lowercase l. Joe, give that lowercase j. We have a conjunction, an and statement. Joe is the cousin of Maria, cousin of, so capital C for the predicate. 2 individuals there. Lowercase j for Joe, lowercase m for Maria. And that is our consequent. Up next will be section 5.6, universal quantifiers. We're still doing our translation games, and the universal quantifier is the next step.